Now question 2, it says the graph shows part of the absorption spectrum of nitrogen oxide N2O, in which the intensity of absorbed radiation of A is plotted against a frequency. So here we get absorption of radiation. You can see it's peaking here. It's peaking there. It means that it's absorbing a lot of energy around the 3.5 times 10 to the 13 hertz. Now, in looking at this, we have for this, it says over here, state the region of the electromagnetic spectrum in which the resonant frequency of the nitrogen oxide belongs. Now, this resonant frequency, obviously, it's the one which is the frequency in which it absorbs or naturally absorbs that frequency. And this is the infrared radiation. This 3.5 times 10 to the 13 hertz, this is a longer wavelength than your visible light. So if we have our visible light here, if that's a visible light, that's light that we can see, on this side over here, if this is increasing wavelength, we have our infrared, I'll call it the IR, and on this side over here we have our UV light. This is our shorter wavelength than our visible light. This is our ultraviolet light. So using your answer in A1, explain why nitrogen oxide is classified as a greenhouse gas. Well, what happens is that the Earth gives off infrared radiation, and this is absorbed by the NO2 and radiated by the NO2, and therefore causes further heating of the Earth. So it maintains or traps in that energy. Moving on to the B part here. We have define emissivity. Now, this comes from these formulas over here. This is your formula for a black body, and this is your formula for a non-black body. And as you can see there, the only difference is this E, and this is your emissivity. Now, this emissivity actually goes from 0 to 1. When you have 1, then this is behaving exactly as a black body, and when it is 0, it means basically that it is not giving off any of its energy. No energy is being given off, where a black body is an object that gives off all the energy due to its temperature. So this emissivity, therefore, is the ratio of the power emitted by a body to the power emitted by a black body. So it's that value. So let's just say we have an emissivity of 0.5. Therefore, if it was a black body, and say it gave off a power of 100 watts, then this over here would only give off a power of 50 watts. So it's that ratio. It's a ratio of the power emitted by a body to the power emitted by a black body. Now we have this question over here. Oh, sorry, I still need to do albedo. Now, albedo is given to us by this formula over here, and so it's a fraction of the energy power incident on the Earth that is reflected. So here we have the total reflected or scattered power as to the total incident power. So you get the total power coming in and the total power that is reflected. So it is that fraction of the energy power incident on the surface that is reflected. So this is the reflected amount. This is the reflected. And this is the total incident power that is coming in, or incident energy. So here we have this situation over here. It says the diagram shows a simple energy balance climate model in which the atmosphere and the surface of the Earth are two bodies, each at a constant temperature. The surface of the Earth receives both solar radiation and radiation emitted from the atmosphere. Assume that the Earth's surface behaves as a black body. So we would use that formula for that. So we get our E, this is emissivity, which is 0.72. So that's the amount that it emits. It's not a black body. That's the ratio as to what it would if it was a black body. And this is our albedo, 2.8, 0.28. So basically that's telling us is that if 100 is coming in, if 100 watts is coming in, 28 is going to be 28 watts will be reflected, and it will allow 72 to go through. So that's what's happening there. So we get our energy is coming in from the sun. Some of it is reflected by the atmosphere. Some of it is allowed to go through to the Earth's surface. And we get these values over here. The average temperature of the atmosphere is 242 Kelvin. The emissivity is equal to 0.72. Average albedo of the atmosphere 0.28. Solar intensity at the top 344. Average temperature of the surface of the Earth 288. We're going to be using those values. So let's do the questions then for this question. It says over here, use the data to show that the power radiated per unit area of the atmosphere is 140 watts per meter squared. So we're going to be using this formula over here. We're going to have the power is equal to E sigma A T to the 4. Now they want the power per unit area, so we want actually that value, so this A is going to disappear. We got our emissivity for this is 0.72. So we have our power is equal to 0.72. Our sigma, this is Stefan Boltzmann's constant. It's equal to 5.67 times 10 to the negative 8 times the temperature, which was 242 Kelvin, and this is to the power of 4. And when we multiply that and get that all right, we get about 140 watts per meter squared. So the solar power absorbed per unit area at the surface of the Earth is 248. Well, for this we are looking at the solar power. Now we are told that the solar power that's coming incident on the outer of the atmosphere is 344, but we get a reflection of 0.28. So this is going to be times 0.72, that will actually be allowed to go through the atmosphere. So when we multiply that out, we get 248 watts per meter squared. Like that. Then D, it says it is hypothesized that if the production of greenhouse gases were to stay at its present level, then the temperature of the Earth's atmosphere would eventually rise by 6 Kelvin. Calculate the power per unit area that would then be radiated by the atmosphere. So we are now looking at if we are increasing our temperature by 6 Kelvin. So again, I'm going to be using this formula over here. Power over area is going to equal our 0.72 as before times 5.67 times 10 to the negative 8. But now we're going to do times 248 because we are raising it by 6 Kelvin. So it was 242, so now 248 squared. And I get from that, I get 154 watts per meter squared. And absorbed by the Earth's surface, well, you are now going to get this amount over here, this 248, but now we'll have this amount that is going to be radiated from the atmosphere. So that will be 248 plus 154, and that would equal 402 watts per meter squared. So estimate using your answer in D2 the increase in temperature of the Earth's surface. So because we view the Earth as a black body, we would be using this formula over here, and the power coming in would therefore be re-radiated over a period of time. So all our energy would be re-radiated because it's a black body. So we get power over area, which is equal to 402 is equal to sigma times T to the 4, and then when I divide this by sigma, I'll get my T to the 4, and this T to the 4, the T works out to be about 290 Kelvin. When I work that sigma, obviously is the same value over here, 5.67 times 10 to the negative 8. So when I put that in, I get 290 Kelvin. So my change in temperature, it went from 288 to 290, so it would be 2 Kelvin. So you're going to get an increase of 2 Kelvin for the surface of the Earth. That will be the increase.